Okay, hi everyone. So we are going to talk about the nomenclature of organic compounds. Why I didn't make that bigger, I don't know. Anyways, it's how to name organic compounds. The book that you use splits naming into about 12 different chapters. So the beginning of every single chapter has a brief introduction on how to name that thing. We're just going to go ahead and rip that band-aid off and learn how to name almost everything right away. So this might feel like a lot, but you can always refer back to this video throughout the semester, and hopefully that will help you. All right, so when you're naming something, the name usually first includes the stereoisomerism, which that's spelled wrong. That O should not be there. Stereoisomerism, like if it's cis or trans, will also eventually do R and S configurations, etc. Then it talks about the substituents, the things hanging off of that molecule. The parent chain, meaning how long that chain of carbon atoms is. The bond type, is it triple, is it double? And then last but not least, the functional group, which we'll get into here in a second. If that sounded like, don't worry, we're going to go through it. Because you generally look at something and you first look at the functional group and then kind of work your way backward, that's how we're going to learn it. So we're going to start with functional groups real quick. All right, so here's a list of functional groups. We got carboxylic acid. So if you have a compound that has a carboxylic acid, it will end with the word oic acid. So for example, something like this. That has a carboxylic acid in it, and it would end with an oic acid. Okay, an ester is this, and don't forget R groups are carbon-containing things. So an ester, if you got something like this to a carbon, let me go like that, and then you double bond to an oxygen, to another oxygen, and then something else hanging off of it, another carbon-containing group. This right here is an ester, and this thing would end with the term oate. An aldehyde, they're generally pretty easy to spot. They'll I'll draw it a little differently than you normally would. They're always going to be a double bonded O at the last carbon. And because it looks funky, a lot of people will write an H there just to remind you, yo, that's an aldehyde, but it's not necessary. It is necessary if you end up using that H in a reaction. Then we have ketones. So like that's anytime you have a double bonded O in the middle of a molecule somewhere that's not on the end. Remember, if it's on the end, it's an aldehyde, and that will end with an -one. Then we have alcohols. Now the alcohol can go just about anywhere. Usually, not usually, sometimes you find them on the end like that, especially ones that you're used to, ethanol, propanol, etc. So the alcohol goes on the end, and that will end with an -ol. I don't know why I just said it goes on the end. It could have gone here, it could have gone here, it could have gone here. All right, then we have amines. Amines are a little funky. Oops, I should have paper behind this. Amines are a little funkier. They end with amine if you have something with an amine, but amine can be anything. It can be like an R group to an N to H to an H, which is what this says. It says, it's a little blurry, but it should say R and H2. We would call this a primary amine because it has one single carbon attached to it. Then we can have a secondary amine where you have something like this. We'll draw the same thing to an N to an H, but this time we'll put like a carbon-containing group on it. So here we have our N. Here's another carbon-containing group. This would be a secondary amine. So even though it doesn't have two H's coming off of that, we would still call it an amine. Then we have a tertiary amine, something like this. Okay, where you have just all three carbon groups coming off of it. So it's anytime you have one carbon, two carbons, or three carbons coming off of a nitrogen. It's called an amine. All right, and that's going to end with amine. Makes it straightforward, right? So amines can have, and it tells you, it can have hydrogen, carbons, or a combination thereof. Halogens, if you're worried that they're missing from the list, like carbon, or like chlorine, fluorine, bromine, etc., don't worry, those come as substituents, and we'll talk about those later. If you remember, substituents were one of the last things we talked about in naming. It's before the stereoisomerism. Okay, so let's go ahead and start by working on functional groups. Let's see if we can find these functional groups. So using our thing here, I gotta rewrite something here. Okay, using our table here, we have something, 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 and an OH. All we're looking for right now is if anything on this table lines up with this. And we have an OH. This is an alcohol. And so it would end with all. When we went and named this thing, it's going to end with all. Okay, now we look at this. Here we have a ketone. Here we have ethers, which aren't on our table. We're not going to worry about them yet. Here we have an amine. We'll eventually learn these as aromatics, but we're not going to talk about them in naming today. Okay, but I asked you to list how you would name this thing. So the order of importance, I told you ethers we're not learning, aromatics we're not learning yet. So pretty much ketones and the amine are the only two things that you can compare. Ketones are here on the list, and the amines are on the next page. They're under it. So amines technically were right here, right? So this list goes in order of importance. Really, I shouldn't say importance. They're all important. Hierarchical naming. So in this hierarchy, this is the one that you'll name first. If you have 2 or 3 of these things, it will end with oic acid. So in this case, we have a ketone and an amine. So the one that's higher up on the list wins. This will end with an ode. Okay. All right, now we're getting to bond type. So single bonds are generally not named. We also have double bonds and triple bonds. So if something has a double bond in it, we name it with an EN. If it has a triple bond in it, it's a YN. And if it's a single bond, it's an A. And it will always end with an A and E. We'll explain why. So this right here, we'll come to know it as butane because it's all single bonds. Here, if we add a double bond to this, we could put the double bond anywhere. We haven't talked about that kind of naming yet. This would be but. We want to write N, but anytime it's all you're writing about something, and there's just an EN, if it ends it, then we'll write an ENE. You'll eventually get to a place where you write EN dash something 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 dash something something something. So in those situations, you just write N. If it's the end of a compound, you write it at the end. You write an E at the end. All right, and then we have this. This is a triple bond. So we want to write this, but again, because it's at the end of this compound, we're going to write an E. So, but the important part is the EN and the YN here. Double bonds are more hierarchical or higher up in the hierarchy than triple bonds. Okay, so let's go through and talk about how we would name these. It says if more double bonds or triple bonds exist, then we can go ahead and use prefixes. So this first one, all we're talking about is how it would end. This would end with an ane because it's all single bonds. This one, hopefully you agree, it's 2 bonds. It's got a double bond there. So it would end with an ene. Here we have 2 double bonds. So here's what we do in this situation. If there's 2 double bonds, our prefixes are di is 2, tri is 3, tetra is 4, etc., penta, hexa, hepta, etc. So there are 2 double bonds, therefore this is a diene. Okay. Here there's 3, so what do you think it's going to be? Hopefully you agree. It's going to be a triene of some sort. And then we get here. What's going on? Well, there are 2 double bonds and then a triple bond. Remember, double bonds take precedent. So this would be a diene. Ein. At the end of the day, a diene. So you got your 2 dienes and then 1 ein. Okay, let's talk about parent. We're doing okay. Breezing through this. Okay. So there's some root words you're going to need to know, particularly up through 12 is usually the highest we go. So if something has 1 carbon in it, we call it a meth. If it's got 2 carbons, its prefix is a eth. If it's got 6, it's hex, etc. Okay. So let's go through and talk about the prefixes these would have. The main thing that you want to do when you're given a chain like this is find the longest chain. The longest chain is not always like left to right. In fact, it's only sometimes left to right. You're always looking for the way that you could start a pen and like go through all the carbons and end up the farthest away, or the counting through the most carbons. So for example, here, if I go here, 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 that's the most carbons. So this would be 1, 2, 3, 4, 5, 6, 7. This would have a prefix of hept. Okay. This next one, you always want to make sure that you're looking at all the possibilities, because it could be that you go here and down and over. But it's not. If you go here, it's 1, 2, 3, 4, 5. But if I go this way, it's 1, 2, 3, 4, 5, 6. And I could have just as easily counted 1, 2, 3, 4, 5, 6. Any way that you wanted to. We get that. This has 6, so this would be a hex. All right, this one. This is getting a lot more realistic and representative of what you'll see. So it might be easy for you to want to go left to right. 1, 2, 3, 4, 5, 6, 7, 8. But if you go this way, 1, 2, 3, 4, 5, 6, 7, 8, 9, you get 9. So you always want to find the longest possible chain. This would be a known. All right, I threw another one in. Has carbons written there. They really didn't need to be written there, but it doesn't matter. If they are, you just count them. So 1, 2, 3, 4, 5, 6, 7, 8 is what I get. If you get something different, let me know, but this would be oct. Okay, count it again. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Another quick way is if you're looking at a chain that's like this, if it goes like this, if it starts down and ends down, that's going to be an odd number. And if it starts down and ends up, that will be an even number in terms of parent chain. Okay, so now we've covered the parent chain. Let's go ahead and look at substituents. So substituents are the things that hang off of a parent chain. So for example, we just did something like do, 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 and then we had something hanging off here, and maybe, I don't know, something, let's go one more here just for fun, something hanging off there. Okay. If I asked you to circle the parent chain, you'd be like, oh, that's this, it's like the longest thing, right? Starts down, ends down, it's an odd number, 1, 2, 3, 4, 5, 6, 7, yep, 7 is an odd number, that's a good check. Okay, and then you ask what's hanging off of this chain. On this chain, we have this group and this group. Those are the substituents. If they're not functional groups, they're going to be substituents. And sometimes functional groups are substituents, and we'll cover that. So I just kind of ask myself what's hanging off of it. Hopefully you agree this is a 1 carbon thing. A 1 carbon thing is a methane, but because it's a substituent, we're going to call it methyl. So this is just a methyl. And here we have a 2 carbon thing, 1, 2. So we call it ethyl. Cool, not so bad, right? So all you're going to do is, at some point, you'll be circling the whole parent chain, and you're going to be asking which substituents come off of that parent chain. A thing that I might as well cover right now is eventually when you go to name this, you're going to put the substituents in alphabetical order. So this particular molecule right here would be something ethyl, something methyl, and then you already know 1, 2, 3, 4, 5, 6, 7. So it would be a hept. And then you also even know that it's all single bonded. Ane. Okay, so we haven't gotten into numbering yet. We'll get there, but right now we know that there's an ethyl, a methyl, and a heptane. So we're getting we're flying through this. Oh, and if I want to go over one more thing. If you come across something where, let's say you have two methyl groups hanging off of it or something to that effect. If we go like this, we go ahead and circle that parent chain. We know it's 1, 2, 3, 4, 5, 6. It's some kind of hexane. And then you just count the substituents hanging off of it. They could be here in the same one. They could be in different ones. What we'd say is this is a dimethyl because there's two of them. Now, when you do di, tri, tetra, etc., these are not used to alphabetized. So, as an example, just to make sure my point's being made, if we have something like this, we'll give it an ethyl group, and a methyl, and a methyl. If this is my parent chain, right, which appears to be a heptane of some sort, we can write it just for fun, just kind of practice it. That's not our goal. Hopefully you agree the substituents hanging off of it is a 1-carbon thing and a 1-carbon thing. So a methyl and a methyl. There's two of them, so we use the prefix dimethyl. And we have an ethyl group right here. The problem is, I told you to alphabetize the substituents, but we don't include the di in alphabetizing. So really it's an M and an E, and these two need to be switched because ethyl comes before methyl. All right, so hopefully that's a decent example. Okay, so now we can move on to other groups. So those are alkyl groups. Alkyl groups are anytime you have some kind of carbon-containing thing hanging off. So they are all substituents, but sometimes it gets a little more complex than just the methyls and the ethyls. We can have propyls and isopropyls, etc. So an example of an isopropyl would be if you had this nice chain, and a propyl would look like this: 1, 2, 3. Okay. So it's just got 1, 2, 3. Some people would call it N-propyl, but it's got 3 things hanging off of it. An isopropyl looks like a little I, right? It's got boop, boop, boop. It would be that. Okay, they're both propyl groups. They both have 1, 2, 3 carbons hanging off of them. But this would be called propyl, and this would be called isopropyl. Then if we have like a butyl group, let's say we have a nice really long chain like this. If we have a butyl group, 1, 2, 3, 4, it'll look like that. You gotta be careful though. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, I just need more on this side. Let's go like this. 10, 1, 2, 3. Okay, cool. All right, we're good. So you have to be careful because the longest chain, right, would have changed the longest chain. It's the danger of coming up with stuff on the fly. So a butyl group would look like this. But if we have a sec butyl group, it would look something like this, where it goes up, 1 goes off, and 2 go over here. This would be sec butyl. I'm going to get another paper because I'm going to run out of space. If we have isobutyl, you would first go up 2 and then branch off. Okay, that's isobutyl. Looks a lot like isopropyl, right? But there's an extra carbon between them. And T-butyl is pretty fun because it looks like a literal T. Sometimes you'll just write T-butyl, but you'll also see tert-butyl. T-butyl is just an abbreviation. So if you happen to have 2 or more of these things, you'd want to alphabetize them, but you have to be careful about alphabetizing them as alkyl groups, because just like the prefixes didn't count in the previous page, there's some things that don't count here. So you ignore when you're alphabetizing. You ignore sec, tert, and then again all the di, tri, tetra, etc. But you don't ignore iso, the methyl part, the chloro, etc. Okay. So now let's go ahead and sorry, I'm going to finish something else. So now we got to go ahead and work on this. Let's see if we can figure out the substituents hanging off of these things. So you can pause it and work on it if you want to. But I'm just going to circle the longest parent chain and then ask what hangs off of it. In this case, it's a 1 carbon thing. This is a methyl. On the next one, even though you might be tempted to circle this, remember you're circling the longest chain, which is that. And this also has a methyl group on it. Now when it comes to these, where you have a halogen hanging off of it, this is chlorine, you would just call that chloro. So this is a chloro and a methyl group, and you would name it as such. Chloro first, then methyl, because C comes before M. With cyclo carbon containing things, the longest chain is always going to be the cyclic one, like this. So it goes around 1, 2, 3, 4, 5, 6, if that makes sense. And the thing hanging off of it is this. That's a substituent. That's an ethyl group. Here, I see another, a bromine. My guess is you know that bromine's going to be bromo, and you would be correct. So you can find the longest parent chain. You can go like that. You could have also started up here and gone down, but that just looked more clean. So here we have a bromo and a methyl. If we happen to have substituents like from these two things together, a chloro, it would be bromo first, then chloro, then methyl when you're writing the name. And then once again, we got this aromatic ring, and we're just looking at the substituents. Here I have a methyl, but what did we call this thing that kind of looks like a Y? It's got 1, 2, 3 carbons in it. It looks like a Y. We call that iso. Propyl. And do we include iso in the thing or ignore it? We should count it. Okay. So in terms of alphabetizing things, we want to include that iso. Ooh, it doesn't end. It keeps going. This is good, because now we're getting even more substituents. So if you remember, we talked about the hierarchy of functional groups. So if I were to look at this sucker right here, I'm like, I see this methyl group hanging off maybe, and if this is like my longest chain right there, cool. But here, hopefully you agree, that's an alcohol. And here we have a carboxylic acid. Well, remember, carboxylic acid takes precedence. This is going to be some sort of oic acid. And that means that this is no longer counted as a functional group. It's now a substituent. So if there's 2 or more functional groups, you only count the highest one, and the other things become substituents. And an OH substituent is called a hydroxy group. It's called a hydroxy group. This over here is a methyl group. So this would be some kind of methyl, hydroxy methyl oic acid. And we get over here, we have another Carboxylic acid, also with an alcohol. So the same exact thing applies. This is a hydroxy group. And this is a functional group, carboxylic acid. It's not a substituent. But it is a functional group. Okay. So we're flying through this. We already talked about, let me pull it up. We already talked about functional groups. We've talked about bond type, if it's going to be an ene or an yne or diene, trine, etc. We talked about the parent, how long the chain is. Is it a hex? Is it a hept? Is it etc.? We've talked about substituents and when to alphabetize them and when not to alphabetize them. Now we're going to talk about stereoisomerism. So, stereoisomerism can get rather complicated, and we're going to bring in that complication in no time in class. But for now, we're going to keep it to just cis and trans. And really, cis and trans give you very minimal details. It's just a quick way to have a general idea of how something works, but it doesn't cover all aspects of that thing. So let's go ahead and do it. If we have a carbon and a carbon bonded, and there's two F's and two H's on them, an F, an F, an H, and an H. Remember, carbon needs 4 bonds, so that would place a double bond between these. Okay, hopefully you agree in this situation that we have a fluorine up here and a fluorine up here. The heavier group kind of takes precedent when it comes to determining cis and trans. So here I have one up here and one up here because they're both up. I call this cis, meaning same. They're like on the same side. As opposed to if I put the F there and this one down here. Now you have a heavy group up top and another heavy group on bottom. They're altered, they're in different sides, they're different, and therefore we would call this trans. Essentially meaning different. Okay. So when we have a double bond, it only ever occurs when you got a double bond, you're going to have something that's either cis or trans usually. So in looking at this, what you do is I like to kind of just draw a line down the middle and then ask, is there something up on either side, or is one thing up and the other thing down? In this case, one thing is up right here and this one's down right here. So this would be trans. On this one, there's a double bond. You got one pointed up in the same direction as the other one, and therefore this is cis. Now I told you things got kind of complicated, and yeah, I probably shouldn't have included these examples. In fact, I'm going to not, but first I did kind of want to go, I could tell you a general answer, which is similar to what I said up here. The heavier thing takes precedent. So over here, and there are some different rules to that, but over here, I hope you agree that this is a 2-carbon thing, and here we got this 3-carbon thing, particularly because it's a carbon bonded to 2 carbons here. This thing's heavier. So this one goes down, hopefully you agree, we see that, and this one would take precedence going down because it's bigger. So if this one's down and this one's down, we would call that cis. And in this situation, this one is down, and this one, the heavier group, is pointed up, so we would call that trans. And that's really horrible what I just did, because you'll know when we get to the end of class, when we get to this, we'll talk about them in totally different terms. But it might help for the future. We'll find out. Okay, last but not least is numbering. And numbering is kind of the biggest pain in the butt we're going to encounter. So I'm going to grab a drink of water before I begin. All right, crew. Numbering. So when you go to number, you always want to remember that functional hierarchy is the first thing that takes precedent, followed by double bond, followed by triple bond. Okay. And what numbering does, if I have something like this, I could label it 1, 2, 3, 4, 5, 6, 7, meaning I'm numbering the carbons a different number. Or I could label it 1, 2, 3, 4, 5, 6, 7. Who's to say which way's right or wrong? And the answer comes down to what substituents, which bonding it has, and which functional groups it has. So functional groups take precedent. You always want to start the numbering toward where the functional groups are. Then double bond, you want to start the numbering toward the closest double bond, and then triple bonds. If it's all single bonds in one triple bond, you start toward the triple bond side. So let's start here with this one. When we go to number it, you already know there's 6 because it tells you. Haha, I just couldn't edit that out without losing some of my triple bond. So here we have 1, 2, 3, 4, 5, 6 things, 6 carbons. That's good. That's what it told us. And when we go to number it, we remember that double bonds take precedent, meaning we want the lowest number to be closest to lowest number. We want the lowest number to be closest to where we start the closest to the double bond or functional group or triple bond in this case. Double bond takes precedent, so the 1 goes here. 2, 3, 4, 5, 6. Okay. So if we went to label this or actually name this thing, we know that it has 6 carbons, right? So it's a hex of some sort. We also know that it has double bonds and a triple bond, but this numbering tells us where that double or triple bond is. So because this is our 1, our double bond was at a 1, this is a 2, and our double bond was at a 3. In other words, we had a 1, 3 di N. And then when we get to 5 to 6, this is where we had the ein. If you remember, we called the double bond was N, and the triple bond was ein, right? So here at the 5, ein. Okay, and so that's kind of how we would label those bonds. If you want to finish it off though, because we might as well, I'll kind of go back to this. We start with the stereoisomerism. If you have 2 or more cis or trans things, you can ignore stereoisomerism for now. Then we had substituents. There are no substituents hanging off of this parent group. Then we have the parent, so we know it's a hex. And then the bond type, which we already wrote out. And then we have a functional group, but there were no functional groups, so this is the end. If you have an end, what do you put on it? An E. And this would be this structure right here. All right. Then we have this one, this fun one. If you remember, this would be a hydroxyl group because this carboxylic acid takes place. This would be some sort of oic acid. So your numbering would start 1, 2, 3, 4. Because you want to make sure that the carbon that is contained within your functional group is the one you label first. All right, then we get down to here. Our longest chain is that. And we could start numbering over here because there's no triple bond, double bond, or functional group, right? But there are substituents. So maybe after this I should say substituents. Okay, so we want to then therefore look for the substituents, which are bromine. You want to get the lowest number possible. So if we started here, we'd go 1, 2, 3, 4, 5. So we'd have a 4 and a 5. But if we go the other way, we'd go 1, 2, 3. That's what we want to do. Okay, so this molecule, we know there's 6 of them, so it'd be some kind of hex something. There is no functional group, there is no bond type, so we're ending with the parent, meaning it's going to be some sort of hexane. And then coming before it would be the substituents. There's also no stereoisomerism. So hopefully you agree these substituents are 2 bromines, which we call dibromo. And they happen to fall at 2 and 3-dibromohexane. That looks really bad. Let me rewrite that. 2,3-dibromohexane. Isn't that rad? Okay. So given that same thing, I think you can do this one relatively quickly. Remember, you want to start the numbering closest to the substituents when there's no functional group, double bond or triple bond. The substituents are next. So here we go, 1, 2, 3, 4, 5, 6 versus 1, 2, 3, 4, 5. You want it to be on a 2 instead of a 5. And you would call this 2,2-dibromohexane. All right, next we get to this last one. We want to, again, make sure you find the longest parent chain because it's so easy to look at this and maybe be like, there's a T-butyl hanging off of it, and then get all excited, or an isopropyl. But you want to just follow the rules every single time. There are no functional groups, right? There is no bond type. There's no double or triple bonds, but there is a parent. So we know that we've got to find the longest parent chain. 1, 2, 3, 4, 5 is what I get. If you get something else, well, cool. So this is going to be some kind of pentane. Now we go to number. You have 2 choices because the methyl group is 2 away on each case, right? So here we have a methyl and a methyl, and here we have another methyl. But if you go this way and you start 1, 2, it's a 2, 3, 4, then you'll end up with a 2, 4, 4 trimethyl. And let's look at if we do the opposite way, if we label the opposite way. If this is a 1 and this is a 2, 3, 4, 5, then we end up with a 2, 2, 4 trimethyl. Only one of them is correct, and it's always going to be the one with the lowest numbers. So the lowest number total is going to be this 2,2,4 trimethyl, and that's why this pentane is in fact 2,2,4 trimethyl pentane. I want to talk about some issues you might run into, maybe 2 main ones. The first one is if you have like because we didn't do any examples, but let's say you have something like this, and let's put an alcohol there. Okay. All right. So if we go to name this thing right here, the longest parent chain, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9. It's some kind of known ine thing. Or is it? Because there's an alcohol. So let's talk. So when you name it, you have to think about all the hierarchy that we've talked about. And we said functional groups take precedent before double and before triple. This is where this comes into play. The functional group's over here. And because of that, you want to start the numbering closer to here, even though the triple bond is also just 1 away. So you'd get the same number, 1, 2. But this is the side you want to start because you want to start with the functional group side. Okay. So when we go to label, this is going to be 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. So in fact, let's name this thing because I think we're probably already there. You know there's, let's pull this up. We know the stereoisomerism isn't there because it's not a double bond. There are no substituents hanging off of it, right? If there had been another functional group, we'd call that a substituent, but it's not. It's a functional group. The parent is 9, so it's some kind of known thing. Dash bond type, well, we know that there's a triple bond at 7, so we would call that 7-ine, right? And we know that the functional group all is on the second carbon, so -2-all. That's how we would name the thing. The other issue you're going to run into is when sometimes you might have the same length. So for example, I was doing one before we started and I almost messed this one up. I was like, let's do this molecule. It looks really cool. And then I started counting and I'm like, Yeah, 1, 2, 3, 4, 5, 6, right? But what if you go 1, 2, 3, 4, 5, 6? Or 1, 2, 3, 4, 5, 6? So which parent chain do you choose? So let's take two different methods, or two different avenues. I'm going to redraw this and show you the difference. Okay. And this first one, if we go, and that's our parent chain, versus this one, 1, 2, 3, 4, 5, 6, right? Versus this as a parent chain. Here we've got this isopropyl thing hanging off. This looks so easy to name because it's got a beautiful isopropyl, super easy substituent. Unfortunately, this is chemistry, organic chemistry, and we're like, hey, if we can make it worse, let's make it worse. This is the one you want to do because it has more substituents. So you choose the parent with the most substituents. And then when we look at starting the numbering, we know that double bonds take precedent way before any substituents. So we would start our numbering 1, 2, 3, 4, 5, 6. Okay. We might as well name it, right? This is going to be some kind of hex thing because, again, there's no stereoisomer. Well, actually, there is stereoisomerism that we're looking at. But this is where I did you a disservice by teaching you the heavy thing. So we're not going to talk about stereoisomerism quite yet. Substituents. So hopefully you agree, off this parent chain, we have an ethyl group here and a methyl group here. Okay. You also have this double bond. So after substituents, then comes the parent. So let's go ahead and list the substituents. We have a 4 ethyl, and then a 5 methyl. Remember, you put them in alphabetical order. E comes before M. So that's the substituents. Then we go to the parent. This is 1, 2, 3, 4, 5, 6. So it's some kind of hex thing. Between the substituents and the parent prefix, you don't actually need a dash. Then, but if you put one, I wouldn't freak out. Then we look at the bond type. We're starting 1, 2, 3. So, ooh, I messed up. Yes, I'm so glad. I'm so glad I can show you guys this. So, dude, you guys, I made just such a rookie mistake right now. I didn't realize that if you count 1, 2, 3, you come into this double bond versus 1, 2, 3, and you come into the double bond no matter what, because obviously it's a 6-bonded thing, so the double bond's in the middle. No matter which way you go, you're going to come into it. Okay, so hold on. Okay, so going back over this, I'm going to redraw it so make sure we're on the same page. Cool. Okay, so if our parent chain is this long thing right there, isn't that beautiful? We want to get the most substituents hanging out. That's why we circled it this way. You want to get the lowest number, right? We just talked about this rule. You want to make sure that you have the lowest number for all the things hanging off of it. And if it didn't matter if we went 1, 2, 3 before we got to the double bond, then you should go in the order that gives you the lowest number for these substituents hanging off. Okay, so now we've got, let's go back to this. Stereoisomerism, we're not going to worry about yet. Substituents, it has a methyl and an ethyl. So now that ethyl is at 3 ethyl, 2 methyl. This is such a good molecule to work with. Okay. Then the parent, again, we know is hex. We don't have to put a dash between that. The bond type, now we're on the bond type. At 3, we got a double bond, 3N. And then last but not least, the functional group, which we don't have. When there's no functional group to add, what do we add to this? An 8. Ooh. You will see, by the way, some common ways that people will write this. They'll write 3-hexene instead. That's not wrong. Okay. It's just another way to name it. But this is the appropriate IUPAC way. All right. I think those are the two things that you'll run into, but I had more than I even thought. It's perfect. Okay, shall we practice? Let's do it. So you're welcome to pause and see if you can name these. Or we're going to do it together. So, starting with the this one right here. The parent chain is 1, 2, 3, 4 long. And remember, you want to start first with labeling the functional groups, the numbers. So the number closest to the functional group would be a 1 there, 2, 3, 4. Now we always go back to this thing. We want to name the stereoisomerism first. There isn't any. The substituents, there's a methyl and a methyl. So we would call that, they both happen to be at 3, so it's a 3,3 dimethyl. After the substituents come the parent. There was 4 things, so it's a bute. The bond type, we didn't have any. And then the functional group is an alcohol. So we would call that 1-all because it happens to be at the 1. Some people might just say butanol, and it's assumed at the 1 position. Okay, then we go to this one. So, always the same things that you're looking for. Parent, 1, 2, 3, 4, 5. Parent chain first. After the parent chain comes the substituents. It looks like there's a methyl group. So let's go ahead and label this first. Do we label from the left, 1, 2, 3, or do you label from the right, 1, 2, 3? Hopefully you remember that the triple bond takes precedent, and therefore we're going to start 1, 2, 3, 4, 5 that way. So it's some kind of pent thing. So substituent-wise, we have a 4-methyl. Then we have, after the substituents come the parent. Again, it was a pent. No dash needed between those. Then the bond type. So this was at 2, we had a triple bond. So we got to say at 2, we had a triple bond. And then there is no functional group, so we just end it with an E. All right, we're killing it. Keep it going. Okay, so with this one, we have 1, 2, 3, 4, 5, looks like to me. I kind of wish that this functional group, this ketone, was over a little more, because then we could talk about labeling. But remember, you always, functional groups takes precedent, so you want to start the labeling closest to the functional group side. Because it's in the middle, this is actually not the best example to show that. But if there happened to be an extra carbon over here, we'd start the numbering over here. Even if there's double bond and other stuff, the functional group takes precedence. Okay, but because there is a double bond, we might as well include it in our numbering, because we know double bond comes before, that's not even a thing, double bond comes before the substituents. So our labeling is going to start over here, 1, 2, 3, 4, 5. And let's go through our process. Stereoisomerism, there is no stereoisomerism. There's an H here and an H here. So it would be it's the same thing. Substituents, we know that there's a methyl at the 4, so 4-methyl. All right, now the parent, 1, 2, 3, 4, 5 we said, so it's going to be pent. The bond type, this is an ene, so this is pent-1 En. And last but not least, the functional group, which we haven't gotten to do until now. This is kind of exciting. There's at the 3, we have a ketone, right? And we call that ketone, we end it with an -one. So this would be -3 -one. Again, that's because it's a ketone. And we know ketone has a suffix of -one. All right. Moving on to this one. You want to start 1, 2, 3, 4. Make sure you have the longest parent chain. Here we have an alcohol. That's going to take precedence, right? Because it's a functional group, so this is going to be an all. So going back through this order, stereoisomerism, there isn't any. Substituents, there are methyl groups. So now we can label it. We know we want to label closer to the functional group side. 1, 2, 3, 4. So it looks to me like we have a 3,3 dimethyl. Oh, I didn't give myself enough space. The parent chain is bute. And then at the 1, we have an all. You might also, again, when it's a 1-all, you might also see that being called butanol as a common name. Sometimes you might even see it 4-butanol if it's on the 4th, but that doesn't really make sense. Sometimes you might see a common name. Let's say you had the alcohol right here. This is 1, 2, 3, 4, 5, 6, 7. So this is a heptane, and we know they start the numbering over here. 1, 2, 3, 4, 5, 6, 7. So you might see somebody calling this thing 2-heptanol versus hept 2-all. This is the more appropriate way. This is just easier for people to say, and it's the older way of writing it. Okay, last but not least, we get to this. 1, 2, 3, 4, 5. Our parent chain is 5. Ooh, I'm glad we're doing this example. Okay. So when we talk about labeling the numbers, if you ever come into a situation where you're not sure, so for example, if I happen to have had a bromine over here, you wouldn't know which way to label. It wouldn't matter, actually, if you had a bromine there. But when in doubt, number along alphabetical lines as well, if it comes into play. This just happened to work out, this 1, 2, 3, 4, 5. So it's some kind of pentane. The reason I numbered it that way was because you had substituents here and here. And if you remember, after you look for functional groups, after you look for double bonds, after you look for triple bonds, then you look for the substituents hanging off of it. So substituents hanging off, you want to number closest to those. Don't forget that we have to alphabetize this. This is a bromo, and this is a chloro. So this is going to be a 2 bromo comes first, 3 chloro thing. So going back to this, no stereoisomerism. The substituents, again, 2 bromo, 3 chloro. The parent was pent. The bonding type, there isn't any. In the functional group, there isn't any. In this case, it's all single bonded, and you'd end it with an ane. Ooh, we covered it in under an hour. That was a goal. Sweet. So hopefully this made some sense to you. Sorry about the mistake in the middle, but it's actually one I'm kind of glad that you guys get to see, and hopefully I hope you were shouting at the camera and frustrated. That actually would make me happy because you'll remember it more. All right, y'all, have a wonderful, wonderful week.